This conference will now be recorded.
Hello everyone, we are starting a new chapter. So this is structure of atom. First we'll see some introductory idea of atomic model. What we understand by atomic model. The word atom, what it means, from which it is derived. It is derived from the Greek word atomos. Atomos means uncuttable. That means further we cannot cut it. And then another word is there. Atom was considered as non-divisible until the discovery of subatomic particles such as electron, proton, neutron. So this word, Greek word atomos, it means uncuttable, or you can say it is non-divisible. So we further cannot divide it. Okay. So that is the concept, old concept. It is not the modern concept, because according to modern concept, there is also some presence of subatomic particles, and these subatomic particles we call them electron, proton, and neutron. Now proton and neutron, these two together, they reside in the nucleus. So nucleus, it consists of neutron as well as proton, and electrons are surrounding this nucleus. Okay. Now remember, this is the modern concept. So we will see that from old concept how we can move towards this modern concept. Okay. So in 19th and 20th centuries, many scientists attempted to explain the structure of atom with the help of different atomic models. So it started from early 19th century, and it is going towards 20th century, and then we have reached some modern concept. Okay. So there are different types of models. Obviously not all the models we are going to discuss. Some of the models we will focus on, but remember, each of these models had their own merits and demerits, because the first model that was developed, that is the oldest model, which is basically the Dalton's atomic model that we have discussed in the previous chapter. Okay, there we have already seen its merits and demerits. So obviously everything will have some demerits, because when the next model is developed, there will be some development, some improvement. So improvement is there. That means obviously in the old concept there is some demerits, or you can say some limitations are present. That is why modern concept is required. So that is why each model has its own merits and demerits, and they both of these are vital for the development of the modern atomic model, because if we know the demerits properly, then only we can remove these limitations and we can further reach towards that is the developed model. Okay. The most notable contributions were made by the scientist John Dalton. Dalton atomic theory we have already seen. Some more will be there, which is J.J. Thomson's atomic model, Rutherford's atomic model, and then Bohr's atomic model. Fine. So see, the three important subatomic particles, electron, proton, and neutron, their that is discovered name is given. J.J. Thomson for electron, proton by Goldstein, and Chadwick for neutron. Fine. So as we know the Dalton's atomic model, we have already learned about it in the previous chapter. Now the next model after Dalton's, that is the next important model, Thomson's atomic model. Thomson put forth his model describing the atomic structure in 1898. It is compared to Dalton's atomic theory, it is later. Okay, based on experiment called cathode ray experiment. Now, based on this experiment, there are some conclusions, and we will see these conclusions one by one. But as a whole, he described the atomic structure as if it is positively charged sphere. That is, you can consider as if it is a homogeneous type of positively charged sphere, into which these negatively charged electrons as if they are embedded. Now you can find some similarity, that is, if we want to know this model properly, just compare it with a watermelon, or you can compare it with a palm pudding. Now why we are giving these examples? Because when you look at watermelon or palm pudding, just see watermelon, the seeds, they will be treated as the negatively charged electron. Or if you consider palm pudding, then these palms are basically these negatively charged electrons. So as if they are electrons. And these electrons, they are as if floating in the sea of positively charged particles, which is actually the pudding. Or if you consider watermelon, the red part, that is the flesh part of watermelon, that is actually the positively charged particles, as if they are spread in overall the atomic model. If you consider, they are spread in the total region, and it is like as if homogeneous, and in them the negatively charged electrons. So you can see the second picture, that is for the atomic model. So this yellow part you can compare with the red fleshy part of watermelon, or the pudding part of palm pudding. Okay, and these electrons as if they are embedded. Fine. So you can compare them to the seeds of watermelon, or if it is palm pudding, then it will be compared to the negatively charged palms. Thomson atomic structure describes atoms as electrically neutral. So if you consider the overall charge of the atom for this atomic model, then it is saying that it is electrically neutral. That means the positive charge and negative charge, they must be equal magnitude. That is why the overall neutrality we can achieve. So the model was able to explain the overall neutrality of atom, because we know that atoms are basically neutral. And from this model also we are seeing that it is neutral. That means this is obviously the merit for this model. The mass of the atom is assumed to be uniformly distributed over the atom. So mass, whatever is the mass, that is not important. The important point is the mass is distributed over the atom uniformly. It is not that in a certain part of the atom the mass is concentrated. No, it is not like that. The mass is throughout distributed over the atom. Limitations. Thomson's atomic model does not clearly explain the stability of an atom and further discoveries of other subatomic particles. So obviously, as we have seen in the previous slide, that every model there is some merits, demerits. So here also you can see the limitation. It does not clearly explain the stability of an atom, though it is saying that it is overall neutral, but no clear, thorough explanation for the stability of an atom, and also further discoveries of subatomic particles, because it is saying nothing about the neutron, but that is also important, subatomic particles. So that is why further discoveries of other subatomic particles, they are completely missing in this model. Cathode ray. Now we have to know what is cathode ray if you want to move further towards modern atomic models. So we have to know what is cathode ray. Here you can see a picture where we have taken a cathode tube through which there is very low pressure. The pressure can be controlled, and through this there will be some gas flowing. So the gas atoms are present under very low pressure. The air inside the chamber was subjected to high voltage. So you can say air or any other gas, it is subjected to high voltage, and electricity flowing through the air from negative electrode to the positive electrode. So negative electrode here, it is basically cathode, which is here, and there is positive electrode. See, this is the positive sign. So this is anode, is mentioned here. So positive electrode, negative electrode, both are present, and it is observed that electricity is flowing through the air from negative electrode towards positive electrode. Fine. Now it is observed that a particle stream or ray, which is in this case we are calling it cathode ray, it is coming out of the negatively charged electrode, that is cathode ray. So just follow this red line, and direction is given towards this side. So this red line, it is moving in a straight line, and it is coming from cathode, coming out from the negatively charged electrode, which is nothing but cathode, towards positively charged electrode. So that is the direction of movement. And further, there is also, we have placed electric field. This is positive, this is negative. So when we have placed electric field, Just before the electric field, it is moving in a straight line, but when it is going through electric field, now there is slight deflection towards positive side, right? So it is not maintaining this straight line direction. Now there is some deflection. So cathode rays, if it is in absence of any electric field, suppose you have not placed this electric field, then its movement will be direct, it will be in straight line, which is shown here in the dotted line. It is in the absence of electric field. But when there is electric field, now there will be some deflection. And here we have some phosphorescent coating, and on that coating we can see this deflection property. The characteristic of cathode rays, which is nothing but stream of electrons, they do not depend on the material of electrodes. So what kind of material you have taken, that is not important here. Okay, and also that is a characteristic of this ray that doesn't depend on the nature of the electrode, and also what type of gas you have taken in this tube. You can take different types of gas, but on the nature of the gas also, the nature of characteristic of these cathode rays, that does not depend. That means there is something which is not dependent on the electrode, as well as not on the nature of gas that is present. It is completely independent of that. So it means that, as we know, electrons, it has nothing to do with what type of element we have taken, that is what type of gas we have taken. Okay, so that is all about cathode, which is nothing but electrons, that is the negatively charged particles. And as it is negatively charged particles, so that is why here you can see the deflection is towards, if you just follow the red line, the deflection is towards positive side, because positive is here, it is not towards negative. So it proves that this ray is consisting of some negatively charged particles. After cathode ray, next is anode rays. Now anode rays, you can also call them positive rays. So the other names also you should know. It is also known as canal rays. It is defined as the beam of positively charged particles. So unlike cathode rays, which is negatively charged particles, right? Now it is positively charged particles. Anode rays are radiations that are positively charged and made up of particles with charges that are equal in magnitude but reverse in sign to the electrons. So you just take one positively charged particle and one negatively charged particle. In both cases, the numerical value of the charges are basically same, magnitude, but sign different. They can also be described as a beam of positive ions produced by certain type of gas discharge tube. So the gas discharge tube that you have just seen in the previous slide, in case of cathode ray, same type of tube also we can take in, and similar type of experiment we can do. But it is now opposite charge. That is the difference. The renowned scientist Goldstein conducted a discharge tube experiment with perforated cathode, and the year is 1886. The anode rays are produced as a result of bombardment of high-speed electrons that are coming from cathode rays. So again, we are using high-speed electrons from cathode rays, and we are applying it on some gaseous atoms. So the basic thing is same that we have already seen in case of cathode rays. Okay, but now these high-speed electrons, what they are doing, they are knocking out electrons from the gaseous atoms. So there are some gaseous atoms and it is bombarded with high-speed electrons. So as a result, the electrons of these gaseous atoms, they are knocked out. So only positive charge in the atom will be remaining. That is the try to understand. In the previous case, there is some stream of electrons coming, there is some deflection. But now what we are doing, these gaseous atoms, they are bombarded with some high speed electrons. High speed is important because we are knocking out the electrons of the gaseous atoms. So that is why high speed is important. And after these electrons are removed from these atoms, obviously there will be some positively ionized ions. Okay, so that is why anode rays are made up of positively ionized ions, which are formed by ionization of the gas. How the ionization of gas is occurring? It is happening because of this knocking out of electrons from them by the application of high-speed electrons that are coming from some cathode ray. Now, some important difference between cathode ray and anode ray. In case of cathode ray, we have seen that this characteristic of this cathode ray, it has nothing to do with the nature of electron or what type of gas you have taken in the discharge tube. But now, anode rays are dependent upon the nature of the gas. So, what type of gas you have taken, that is now important. Fine. And mass of anode rays, it is almost identical to the atoms from which they are derived. That means what type of gaseous atoms you have taken, that is also important here, because on the nature of these gaseous atoms, the mass of anode rays, that is dependent. But this type of thing we have not seen in case of cathode rays. Fine. If we compare cathode rays and anode rays based on some properties that are mentioned in the left hand side table, motional, they travel in straight line. Anode rays, they also travel in straight line. So this is similarity. Type of charge, now this is different. They are deflected towards positive plates, which means they are negatively charged. They are deflected towards negative plate, that means they are carrying some positive charge. Particles present in cathode rays, they are basically electrons. So though we are calling it cathode ray, but actually these particles are known as electrons. And for anode rays, the particles present, they are known as, it is basically known as, you can say protons, because positively charged particles we call it protons, right? But initially it was simply called positively charged particles. Quantity of charge and mass. Electrons present in cathode rays, they have same charge and mass. So whatever is the source of electron, that is what type of gas you have taken, it will always, that is independent, that is irrespective of that, the electrons that are present in cathode ray, their charge, mass, all are same for all the electrons. So individual electrons, they are having same charge and same mass, and the charge on the particles depends upon the number of electron lost by the atoms. So basically, though I have said that previously it is actually protons, but exactly you cannot say it is protons, because when we consider it protons, there is some fixed mass and charge. Fine, but here that is not the case. So better you say anode rays as positively charged particles, beam of positively charged particles, because the charge on the particles, that depends on the number of electrons lost by the atoms. So if it is losing 1 electron, then the charge will be +1. If it is losing 2 electrons, the charge will be +2. Okay, so it may vary. Origin, they origin from cathode, they origin from anode. So these are some of the similarities or dissimilarities between these two different types of ray. After Thomson's atomic model, the next important model is Rutherford's atomic model. He conducted an experiment in 1911. How? By bombarding a thin sheet of gold. So here you can see this yellow thin sheet of gold, and it is bombarded with alpha particles. Now what is alpha particles? Because we are seeing it first time. So alpha particles are basically helium-2 plus. You know helium element where atomic number is 2, that is the next element of hydrogen. So when it is, we are calling it alpha particle, it is basically helium 2 plus. And so we are now bombarding this thin sheet of gold with alpha particles. So after bombarding with these alpha particles, then we are considering or studying the trajectory of these particles after their interaction with the gold foil. Rutherford made certain observations that contradicted Thomson's atomic model. So see, as I have said, Thomson's atomic model, it is previously done. If you come look at the year, so when some further development is going on, obviously the previous model, we can find some limitations, and some of the limitations also we can overcome. So these helium-2 plus particles or alpha particles, now it is bombarding this thin sheet of gold, and there are, we can see some deflection. So there are some particles without deflection. So see, it is in straight line. Fine. There are some particles that are scattered. Just follow this line. And there is a very few amount where the deflection, it is with a very high angle. So as if it is almost 180-degree deflection. So it is coming like this and it is having as if it is taking a U-turn. So it is almost 180-degree deflection. These are also deflection, but here angles are not so high. And there are some deflection where angle is very high, almost U-turn. And particles also there which is having no deflection. So three different types of things we can see. So observations, if we mention it in simple points, a major fraction of alpha particles pass through the sheet without any deflection. So most of the alpha particles or helium-2+, most of the alpha particles or helium-2+ pass through the sheet without any deflection. So see here the line that you are seeing, it is very that is compared to the other lines, you can see it is concentrated compared to the other lines, because in other lines they are comparatively thinner. That means very high number of helium-2+ ion particles are present. So that is why the particles without deflection, though you are seeing here only a single line, but basically it is combination of several helium-2+. So that is why the line is so broad. So major fraction of the alpha particles that we are supplying towards this gold foil so that it can bombard it, most of them there is no deflection. Okay, it is simply going through this gold foil. Some of these alpha particles deflected by the gold sheet by very small angle. So just focus on these alpha particles. There is very small angle deflection. So just consider this point with respect to this angle is not very high. But if you, with respect to this point, if you consider this deflected, the angle is now very, very high, right? So very few of alpha particles deflected back, that is only a few alpha particles, as if it is 180-degree angle of deflection. So it is just going and coming back. So that is, it is 180-degree deflection. This angle is very high. So these are the observations for this gold alpha particle experiment. Now from these observations, what conclusions we can draw, that we will see now. So here you can see different alpha particles, 1, 2, 3, 4, 5, 6. So out of these 6, look at the second one, it is passing straight. That means now in the previous case we have taken simply gold foil, but now we have enlarged the atom. So you can see in the center of this atom there are total 4 atoms we have taken here. Center there is nucleus. So you can see the positive charge. And you can also see the negative charge that is surrounding this gold foil. Sorry, surrounding this positively charged nucleus. So when these alpha particles, these are the alpha particles, as I have said, it is helium-2+. So that is why there are 2 positive charge present. So this helium-2+, it is passing straight. Now when it can pass straight, because it is itself carrying 2 positive charge. And if it is far from this nucleus, there will be no repulsion, because nucleus there is positive charge and helium-2+ is also positive. So if it is very close to the positive charge, then only there will be some repulsion. But if it is not close to the positive charge, there will be no repulsion. Fine. So it is passing straight. Then another possibility is when it is slightly close to the nucleus. See here it is not close to nucleus, but when it is slightly close to nucleus, there is deflection. So here you can see deflection, and when it is very close to the positive charge, there is large deflection. Fine. And when it is directly hitting this center nucleus, so this amount is very less, because it is directly hitting positive. So out of, I mean to say, several alpha particles are there, but out of the several, only a few will be hitting directly and they will be turning back, 180-degree deflection, but most of them passed straight. That means there is some vacancy Nothing is there, no positive charge, no negative charge. Now, what are the conclusions we can draw? The positive charge and most of the mass of an atom is concentrated in an extremely small volume. So that is why most of the helium 2 plus particles, they are passing straight, most of them. So see, pass straight, pass straight, pass straight, most of them. He called this region, that is Rutherford called this region of the atom as nucleus. So in this way, nucleus is discovered. Size of the nucleus of an atom is very small in comparison to the total size of the atom, right? So that is the reason. Just focus on this. It is turning back because it is directly hitting. But that is a very rare case. And rare case, when we can say, when this center, it is having very small size compared to the overall size of the atom. Because if it is very large size compared to overall size of the atom, then this type of incident, that is 180-degree turning back, that will also be very high. But as the center, it is in very small region, so that is why out of several alpha particles, only a few is turning back 180 degree. So it proves that the size of nucleus of an atom, it is very small. It is concentrated in a small region in the center of the atom. The negatively charged electrons surround the nucleus of an atom and revolve around it with very high speed in circular path, and these are known as orbits. Electrons and neutrons, how they are that is existing together, it is because of the strong electrostatic force of attraction. And overall, the atom, the charge of the atom, it is neutral because of these oppositely charged particles presence. Electrons are present, protons are also present. Actually, proton, this term we are not using. We are just saying this positive charge that is present in the center. Fine. So these are the conclusions of alpha scattering experiment. Limitations of this atomic model. So just like Thomson's atomic model, here also we can see some limitations. When a body is moving in an orbit, remember in the previous slide we have mentioned that these electrons, they are moving in circular path and they are orbit. So when a body is moving in a circular path like this orbit, it undergoes acceleration. So here these negatively charged particles, they are moving in an orbit by and having in the center the positive charge. So when this type of thing is happening, there will be acceleration. So it is true that they are moving in constant speed, but as they are changing their direction, it is circular. They are changing their direction each moment. So that is why there will be acceleration. Without acceleration, they cannot revolve. Okay. So when a body is moving in an orbit and it is charged body, there will always be an acceleration because each moment they are changing their direction. Now, according to electromagnetic theory, when a charged particle is accelerated, it should always emit electromagnetic radiation. So this is already there is some observation from electromagnetic theory. If there is some acceleration happening in some charged particles, just like here electron is negatively charged and there is some acceleration happening. So electrons should also emit some electromagnetic radiation. Okay. Now when they are emitting radiation, and the energy of this radiation is basically coming from electronic motion. So when they are emitting radiation, there will be some loss of energy. So electronic motion, that will be gradually slow and slow. So when this motion will be slow, they will fall on the nucleus, right? Because gradually their motion is becoming, speed is becoming less and less. So one time will reach when they will lose all their energy and it will fall into the nucleus, and as a result the atom will be collapsed because there will be no stability present anymore. But this actually doesn't happen in reality, right? So this observation is not matching. Then some other points. Okay, before that, look at this picture. Here, this blue part, that is actually the nucleus. The red dot, that is the electron. And when the electron is moving in this circular path, then gradually it will fall in the nucleus. So this will be its ultimate fate, because each moment they are losing some radiation. So there is loss of energy. So ultimately the electron will fall on the nucleus, and that means collapse of atom. There are some other points for limitations of this model. It says nothing about the distribution of electrons. It is simply saying that electrons are moving in orbits surrounding the nucleus. But what is the proper distribution of electrons around the nucleus, and what about the energies of these electrons? It is saying nothing about that. If electrons continuously revolve around the nucleus, the type of spectrum that we expect is continuous spectrum. But in reality, line spectrum is observed. Now, right at the this moment, you will not be able to understand what is continuous spectrum or line spectrum. Just remember this line, that in reality line spectrum is obtained. But if you simply follow this model, it should have continuous spectrum, but that doesn't happen in reality. So these two types of spectrum, it will be discussed later, not now, and then you will be able to understand it properly. Now you can ask one question, that if electrons are moving their charge and there is some collapse happening, which is not at all we can see in reality, then why we are not considering the electrons as if they are stationary? Suppose when we are considering it is moving, we are seeing some problem which is not matching with the observation that we see in reality, then we can simply consider the electrons as stationary, right? But the answer for this question is, if you consider electrons as stationary, obviously there will be some electrostatic attraction between the dense nucleus. Dense means dense positively charged nucleus, and the electrons would pull the it will pull the electrons towards the nucleus. Because electrons are stationary, there is some positively charged particles in dense region, that is the center. Obviously it will draw the electrons. If it is not continuously moving, if it is stationary, it will draw the electrons, and ultimately what will happen, as if in the center now both positive charge, negative charge, everything will be present, just as if it is a mini version of Thomson's model. Because in Thomson's model, what we have seen, the whole atom as if it is homogeneous sea of positive charge, and in that sea of positive charge there is some electrons embedded. So that is the picture for the whole atom. But now, as the negatively charged electrons, they are towards the center, so as if only in the center there is some positive and negative charge present. So that is why we are saying it is a miniature version of Thomson's model, but that is also not the reality. So whether you consider electrons as stationary, then also you are not reaching any meaningful conclusion. And when you are considering their in acceleration, then also there is some problem of collapsing of the atomic model. Okay, so from both point of view, it is not what, there is some limitations. After this model, we'll see how neutron is discovered, because we have seen the discovery of positive charge, negative charge, cathode ray, anode ray, but nothing about neutron. So how it is discovered? In 1932, James Chadwick conducted an experiment in which he bombarded beryllium with alpha particles. Beryllium, which is, remember its symbol is Be, it is bombarded with alpha particles, the same type of particles that we have used in Rutherford's experiment. During this experiment, he discovered the emission of neutral radiation. Chadwick's discovery of neutral particle or neutron led to the current understanding that the nucleus is made up of protons and neutrons. There is some further development in the concept of nucleus. Neutron is neutral subatomic particles. Electron, protons, they are also subatomic particles, but they are not neutral. But neutron is neutral with no electric charge, and if we talk about mass, they are having mass same as that of proton. Okay. So in a nutshell, there are three important subatomic particles: proton, positive, electron, negative, and neutron, which is neutral. So they are the three important constituents of an atom. So here in this table, you can see all the informations together. Electrons, you can express it in different way. You can express it simply mention it as E. You can write it in this way. 0 means here it is having no mass, and -1 means it is having charge -1. So charge is -1. Or sometimes it is also written as beta particle. Mass is 0, which is in the superscript, subscript -1, which means charge. Now its mass is 1/1872 fraction compared to AMU, which is almost close to 0. It is very, very small, as if it is 0. So it has no mass as location outside the nucleus, and there are some energy levels present, details of which we will see later. And for protons and neutrons, in both cases the mass is same. Another similarity between them, both are present in the nucleus. So mass of protons and neutrons 1 AMU, but compared to the mass of neutrons, electrons mass is very, very less, almost is 0 AMU, atomic mass unit. Protons, it can be expressed simply P or 1p1, that means mass is considered as +1 and charge is also +1, or you can simply express it as if it is hydrogen atom. So it has some similarity with hydrogen atom, because in hydrogen also it is only one proton. So that is the reason we express it in this way. And neutrons, simply mention it as N or 1 and 0. Why 0? Because it has no charge. So that is why in the subscript there is mentioned, we have mentioned 0, and 1 is superscript because of the mass. Now look at this value of mass and charge. If we see mass for proton and neutron, it is same, 1.67 10 to the power -27. This order is most important. And if you look at the mass of electron, it is 10 to the power -31. So there is huge difference in the power of 10. But if you consider charge, there is no charge for neutron, but these two, their charges are magnitude same, but sign is different, negative and positive for electrons and protons respectively. We'll also see what is the further development after Rutherford's atomic model. But before going to that, discussion of these other things that we are doing now, that is important. So that is why the next development in the model, it will take some time. Okay. So in the meantime, we are seeing some other topics. So after new discovery of a neutron, next we have to know atomic number and mass number. Though some introductory idea we have already seen in the previous chapter, some basic concepts of chemistry, but here we'll go in details. Atoms of each element contain a characteristic number of protons that are present in the nucleus, and this determines what atom we are looking for. So if you know the atomic number, you can easily identify which element you are talking about. So that is why it is important for us to know. The number of protons in an atom or the number of electrons in an electrically neutral atom is called atomic number, and it is represented by Z. Though it is proton, and proton we express by P, but when you are talking about atomic number, which is basically the total number of protons, or you can say the total number of electrons, because always the number of protons equal to the number of electrons. So if you know the atomic number, basically you also know the number of electrons. But remember, it is applicable only for electrically neutral atom. If it is not neutral, if it is carrying some positive charge, then you cannot say that number of protons equal to number of electrons. It is only applicable for electrically neutral atom. So for electrically neutral atom, if you know the value of Z, which is atomic number, basically you know the number of protons, you also know the number of electrons. How we express it? So the general picture is X. Suppose X is the element, A is mass number, Z is atomic number, which is nothing but number of protons. So just compare as if X is here C, Z is here 6, and mass is A, capital A, which is 12. So carbon, this element we have taken as example. So X is basically chemical symbol. And what is mass number? Mass number is expressed by capital A, which is summation of Z plus N. Z is atomic number, that is total number of protons, and N is total number of neutrons. It can also be written like this. small p plus small n. That is also basically mass number. Sometimes it is also mentioned as capital M. Fine. So in this way we represent any element. So in this representation, simultaneously you can understand what is the atomic number. You can also understand what is the mass number. And if you simply deduct atomic number from A, that is, if you simply do this A minus Z, what you get? You get N, because A is Z plus A. So N will be A minus Z. So you can also identify what is the number of neutrons. In contrast, the number of neutrons for a given element, it can vary. So suppose you have taken different atoms of same element. There may be some difference in the number of neutrons, but number of protons for a given element, it will be same. Because when the number of protons change, element itself will be changed. So number must be same. That is, atomic number must be same if the element is same. But number of neutrons for a given element, it can vary. That means A can also vary, mass number. The number of protons and neutrons combine together to give mass number, which is represented by A. So mass number is equal to protons plus neutrons. And as these two types of particles, they are present in the nucleus. So collectively, that is, together you can call these two types of particles nucleons, because they are present in the center, in the nucleus. Another example, here we have taken the element cobalt. So this is the chemical symbol of this element, capital C, then O. Mass number is 59, atomic number is 27. So here A is 59, then Z is 27. That means N should be 59 minus 27. So in this way you can identify A, Z and also capital N. That is the number of neutrons. Isotopes and relative atomic mass. Now isotope, initial idea we have already seen in the previous chapter, which we have finished in the last class. But now we will see some details of it. Carbon 6C. We have already seen how we have represented it in the previous slide. But now we will also see the isotopes of carbon. So isotopes of carbon, here we have taken 13C6, 14C6. So the definition of isotope is number of protons same. So see, 6, 6, 6. There is no change in the number of protons, because once you change the number of protons, element will not be same. It will be some different element. Suppose it is, you are changing it from 6 to 5. It will be boron. You are changing from 6 to 7. It will be nitrogen. Fine. But mass number may change. So these three species, they are related to each other as isotope. Now how they are different? Proton number is same, right? You can see this yellow color. These particles, they are basically positively charged and they are proton. So in each of these three picture, three atoms, number of protons 7. That is this yellow part. But neutron, which is these pink balls, here it is 6, right? Here it is 7. Here it is 8. So how you are getting it? 12 minus 6. That means it is 6. Then 12, sorry, here it is 13. 13 minus 6. So it will be 7. In the last case, it is 14 minus 6. So it is now 8. So neutron number is different. Proton number is same. And obviously electron numbers same, because it is always same to the number of protons. So this is the definition of isotope, where number of protons same, but neutron number different. Isotopes are atoms of the same element that have different number of neutrons but same number of protons. That condition must be fulfilled. Difference in the number of neutrons between the different isotopes of an element, it means the masses will also be different. So that is why you can see here three different mass: 12, 13 and 14. Now if we talk about the chemical properties of atoms, they are controlled by the number of electrons. and you know the number of electrons that is determined by the number of protons. So you can also say in another way, chemical properties, they are controlled by the number of protons. But directly, if you consider chemical reaction, these electrons are basically taking part. So that is why we say it is better to say that chemical properties are controlled by number of electrons, and that is controlled by number of protons, because these two are always same. Number of neutrons present in the nucleus have very little effect on the chemical properties of an element. So that is why chemical properties of all these three isotopes of carbon, not just for carbon, if you consider any other element and their isotope, there is no effect on chemical properties. So when you change the number of neutrons, no effect, very little effect on the chemical properties, almost nil. So that is the reason all the isotopes of a given element, their chemical behavior should be same, because it has nothing to do with the number of neutrons. Electromagnetic wave theory. What is electromagnetic wave? We'll try to have some primary idea. Though it is very details, we are having here very simplified idea. James Maxwell, he is the first to give a comprehensive explanation about the interaction between the charged bodies and the electrical and magnetic field on macroscopic level. So important thing, macroscopic level, large object, not for microscopic objects. And it is charged body, how it is interacting with electric field, magnetic field, that is all about this theory. He suggested that when electrically charged particle moves under acceleration, remember this thing we have already seen, because electron, they are electrically charged, they move under some acceleration. So when it happens, there is alternating electrical field and magnetic fields generated and transmitted. So here in the right hand side picture, you can see the magnetic field in the orange color, and or in the green color, that is the magnetic field, and this one is the electric field. Now these two are perpendicular to each other, and if this is the direction of the propagation of wave, then magnetic field is 90 degree to the direction of propagation, and the electric field is also 90 degree. So this angle is 90 degree, right? And this angle is also 90 degree. So individually both of them are 90 degree to the direction of propagation, and magnetic field, electric field, they are also 90 degree to each other. If you are having some trouble to understand this, you can consider as if it is x-axis. In 3 dimension, it is y-axis, it is z. We know these 3 axes, they are perpendicular to each other. So as if x is the direction towards magnetic field, y is for electric, and the direction of propagation is z. So that these 3, they are 90 degree to each other. These fields are transmitted in the form of waves, which is known as electromagnetic waves or radiation. Example is light wave. Now, unlike sound wave or wave in water that we know, these waves, light wave or electromagnetic wave, they do not require any medium. They can move in vacuum. This is important difference with other types of wave, sound wave or wave in water. There are many types of electromagnetic radiation which differ from one another. How they differ? They differ in wavelength or frequency. Now, what is wavelength? What is frequency? That we have to see now. Here also you can understand it. As you can see here, if you consider this point of wave, and then it is going downward, again it is moving upward, and this is the repeating pattern. So if you take this distance, this will give you the wavelength. So if these 2 points, they are very close to each other, now it will be very narrow, wavelength will be short. So this is wavelength. So in the next slide you will see what is frequency, what is wavelength. So frequency is defined as the number of waves that pass through a given point. So suppose when it is moving and there is some particular point, if you consider, then another wave is there. Now it is very narrow to each other, still the point is here. So another wave which is very large wavelength, Now the point is here. So more the wavelength, it is becoming narrow and narrow. That means wavelength is reduced. Now what will happen? Through this given point or a particular constant point, the number of waves passing through in 1 second, unit second, obviously this will be increased. So when wavelength is decreased, so see here wavelength is very high, then here wavelength is comparatively less, and in this picture it is very less. So as it is becoming less and less, frequency is becoming high, because now through a common point the number of waves generated in unit second, that is very high, because the definition of frequency is it is the number of waves that pass through a given point in 1 second. But mathematically it is equal to reciprocal of the time period of electromagnetic radiation. So that is why its unit is second inverse. Wavelength can be defined as the distance between two successive crests or troughs of a wave. So this uphill movement, downhill movement, these 2 points, one is crest, another one is trough. You can consider the lower part maximum or the upper part maximum, any two you can consider, but this distance that will be known as wavelength. So this is the wavelength, how it is, you can see in this picture very clear, and it is one oscillation. So it is moving upward then going downward, it is completing one oscillation, fine. And frequency is the number of oscillation per second. So when the wavelength is narrow, that means these 2 points, they are coming close to each other. That means when they are very close to each other, wavelength is becoming short and short, but frequency is the number of oscillation per second. So now per second this oscillation will increase. Or you can also consider this definition, which is even, it is comparatively easier to understand. And this is amplitude or power. So this distance, that is this maximum from this line, how far it is, that is actually amplitude. So suppose another wave, it is like this. So now it is having higher amplitude, or another wavelength if it is shorter, it is lower amplitude. So these are the different terms you can see. So 2 waves are there, you'll be able to understand the difference, what is long wavelength or short wavelength. So when long wavelength, now that means just consider the distance between 2 crests or 2 troughs. In this case we have taken crest. And short wavelength means now they are close to each other. So when they are close to each other, frequency is high. When they are far from each other, frequency is low. That means wavelength, which is denoted by lambda, and frequency, which is denoted by mu, they are inversely related to each other. When frequency high, wavelength less. When wavelength high, frequency less. If you solve this simple problem, the idea of frequency, wavelength, and another term is also there, it is also used, wave number, it will be clear, the idea will be clear. So frequency, as we know, its unit is second inverse. So obviously it will be 1 by time unit. So suppose the time in which we are considering this wave, it is 5 into 10 to the minus 10 second. To do this calculation, you will get the frequency. See, it is 0.2 into 10 to the power 10 per second. Now wavelength, as it is related to mu, we know it is inversely proportional, but if you remove this inverse sign, then lambda will be equal to c by nu. C is the constant velocity of light. Put the value of c, 3 into 10 to the power 10 meter per second, and nu we have just calculated, it is 0.2 10 to the power 10 per second. So look at the value of wavelength. Frequency is so high, clear from the power of 10, but wavelength, it is less. And what is wave number? Wave number is that is inverse of lambda. So that is why we know the unit of wavelength is distance unit. It may be meter, it may be angstrom, nanometer, like this, picometer. So obviously now the wave number, it will be meter inverse or angstrom inverse or picometer inverse, like this. So what value we have obtained for wavelength? It is 15 into 10 to the minus 2. So for wave number, it will be 1 by 15 into 10 to the minus 2. So the value is 6.66. So in this way you can understand the relationship between frequency, wavelength and wave number. So we have very less time, so I will not start it today. So there will be some problems related to frequency, wavelength, so that your idea is more clear. So we are ending it here. Some more discussion will be there in the next class. Thank you for listening.